Hello. How's everybody doing? Happy Friday. Let me know who's here. Say hi in the chat. A lot of you here already. What's got into you? 3 minutes early. Oh, people are leaving. Happy Friday, Nicole. Hello, Reagan. Good morning, Jax. Navik, good to see you again. Hello, Jared. Turner, nice to see that your chat is working this morning. Good morning, Giannis. Hello, Jonathan. Good morning. I hope that this isn't instant coffee. No way. Come on. Only the real stuff. You're not late. Class starts at 10. We'll get started in a few seconds, I guess. Oh yeah, there's no class last Friday. That's true. All right, well, it's 10 o'clock, so we could get started. So I hope you are all prepared with your coffee or your tea or your water, Gatorade, Red Bull, whatever people are drinking, to join me in the simultaneous sip, the best part of the class. Good stuff. All right, let me see in the chat who joined in on the sip today, especially when you have a quiz in 40 minutes. It's good luck to sip. James and Max. A lot of people sipping today. Jonathan and Navik with the emojis. Reagan, Lauren, Jax, Grace, Nicole, Nathaniel. Jared slurped the whole thing. Turner, no sip. I appreciate the honesty. Johannes, Inman, Logan, Ellie. Everybody's sipping today, it seems like. Okay, so I'll write out an example, then I'll keep reading through all these. So let h of x be the integral Will and Bella from 1 minus 2x to 1 plus 2x of t sine of t. The question is, find h prime of x. Okay, so we have the integral h of x is the function that's the integral from 1 minus 2x to 1 plus 2x of t sine of t dt. We want to find its derivative. Which theorem do we use in order to find the derivative of an integral? So that's the question. What theorem do we use to find the derivative of an integral? Yeah, we're going to use the fundamental theorem, part 1, actually. Yeah, so there's the 2 parts to it. We're going to use the first part, which tells us how to take the integral when you have a constant as the bottom and you have x up top. Right, but here we have a function and a function. Here we have a function and a function. What can we do to this integral in order to make one of the bounds not a function? Can we make it a constant? Maybe this is a hard question to ask, especially when you have to answer on a computer. So I'll just kind of show us what we'll do. Remember, we had an identity that said instead of taking the integral from here to here, we could stop somewhere along the way and break up our integral into 2 integrals. So we could rewrite h of x as the integral from 1 minus 2x to, let's say, 0. It doesn't matter which constant we pick here. We just have to pick a constant. Plus the integral from 0 to 1 plus 2x. All right, so this was one of the integral identities we stated yesterday. And this part here we could use the fundamental theorem of calculus part 1 on, because we have a constant on the bottom and we have a function up top, so we know how to take this derivative. But here we have a function on the bottom and a constant on top. How can we fix this? So what can we do to this part, this first term, in order to get a constant below and a function up top? Flip the bounds and make the integral negative. Yes, exactly. We could switch the order of the bounds, but it comes at the cost of a negative sign. So negative integral from 0 to 1 minus 2x. So we have this. And now we know how to take the derivative of these. So by the fundamental theorem of calculus part 1, we know that the derivative of this function here, you replace every t with 1 minus 2x. And then you have to multiply by the derivative of this function. So we're using the chain rule here. And I'm out of space, so I'm going to just continue writing down below. And now the same thing here. You replace every t with 1 plus 2x. And then you multiply by the derivative of this function. And so this is the derivative of this integral. Okay, and so I have a video that does a question similar to this. So take a look at that if you want another example of using the fundamental theorem of calculus part 1. This is like as hard as it's going to get in terms of what you could see with using this theorem. All right, so let's take a look at another example. This will be using FTC2. So find the area under the curve f of x equals cosine of x. From 0 to pi over 2. Okay, so does somebody in the chat want to say, what's our easiest method for solving this problem? So those of you who have taken AP Calc before and know the shortcuts, I'm asking, what is the shortcut? Or those of you who were in class yesterday and saw that we had the Fundamental Theorem of Calculus Part 2, how do we find the area under the curve of this function with these bounds? Yes, find the antiderivative. Okay, so really what we want to do, a late sip coming from Mr. West 39. What we want to do is we want to evaluate the integral from 0 to pi over 2 of cosine of x dx. Okay? And so, as Bella said, we want to find the antiderivative. What is the antiderivative of cosine of x? Yeah, the antiderivative of cosine of x is sine of x. And we want to evaluate, so I'm going to use some notation that we'll use quite a bit. It's a vertical line. And it says we want to evaluate at x equals pi over 2 and x equals 0. Okay, so remember, the fundamental theorem says the value of this integral is sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. So the area under the cosine curve in that first kind of section of it, right? If we sketch the cosine curve, this section here has area 1. That's what we just showed. Right, and if you can look back in your notes, we actually tried to solve this question using Riemann sums, and we just stopped because it was too hard. But with the fundamental theorem of calculus, come on, what'd that take us? 15 seconds? With the delay. All right, let's take a look at another example. All right, this example, the chat is just out of hand today, which is better than what it was yesterday where it was just silent. So this example is, what is wrong with the following calculation? All right, so what is wrong with the following calculation? I'm going to write out, what looks like some good math, and you all have to tell me why it's fake math. Okay, that's the plan here. Well, we want to evaluate the integral from -1 to 3 of 1 over x squared dx. Okay, so we want to evaluate. We want to evaluate this integral from -1 to 3, and I claim, well, what do? We find the antiderivative of x squared. So it's finding the antiderivative of x to the -2. We increase the power by 1 and divide by the new power, right? And then we evaluate at the endpoints. Which gives us -1/3 minus -1, which gives us -4/3. Okay, but let's just see if this makes sense. I mean, I'm telling you, there's something wrong with the calculation. Why should we know it's wrong? Well, if we sketch the curve y equals 1 over x squared, it looks something like this. And so if we go from -1 to 3, we'd be finding the area of this region, which is all above the x-axis, right? So the answer should be positive if we did it correctly, but we got -4/3. So what's wrong? Where did we go wrong? Right, we have a function, we found its antiderivative, we plugged in the endpoints, and we took the difference, and we got -4/3. Right, maybe, so something went wrong. I think our drawing is good, so it's not the drawing that went wrong, it's somewhere along here. Does anybody have any ideas? Yeah, exactly, Jax. What did the fundamental theorem of calculus say? It says we have to have a function that is continuous on our interval. So, right, this is not continuous on our interval. Our interval it's discontinuous at 0. So and 0 is inside of our interval. So yeah, the fundamental theorem of calculus doesn't apply here. And yeah, what Navik says in the chat is correct. The way you would evaluate this integral is you would split it up, kind of like we did here. You would split it up at the discontinuity. You'd split it. You go integral from -1 to 0 plus the integral from 0 to 3. But that's going to be probably how you start Calc 2 next semester. So for now, we'll just say that this integral, we're not sure how to solve. Yeah, so that what's wrong with it? We need our function to be continuous on the domain. All right, so we'll move on to another example. I guess here's a question for you in the chat. Can you hear my neighbor's dog barking? Because he seems very excited about this example because he started barking right when we started writing it and hasn't stopped. All right, here's a quick one for you. Uh-oh, Johannes could hear the dog. Well, you know, we have some extra company today. All right, so this one is pretty quick. Evaluate the integral from 1 to 9 of the square root of x dx. And if you get an answer or you have some ideas of how to start the question, feel free to share those in the chat. All right, so maybe some of you aren't sure where to get started. That's okay. So just remember, the square root of x is that's our notation for writing x to the 1/2 power. So for this class, and you know, life in general, I would say, it's probably best to just leave it like x to the 1/2. So really what we're trying to do is find the integral from 1 to 9 of x to the 1/2 dx. Okay, and so we'll increase the power by 1, divide by the new power, and evaluate at the endpoints. So that's 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2. 9 to the 3/2. Well, 9 to the 1/2 is 3, and 3 to the 3rd is 27. 1 to any power is 1. So we have 2/3 times 26, or 52/3. So is it clear? Can I get a reaction in the crowd if we're good with this type of question and can move on, or do you want me to go over it again? Jack says smiley face. That's good. We'll be doing plenty of integrals next week. Thumbs up. Smiley face from Turner. Excellent, excellent. Jonathan with a big smile. He loves these questions. That's great. Okay, let's move on to section 4.4. I mean, all these, 4.3, 4.4, 4.5, they're all kind of a continuation of each other. So this is indefinite integrals. So basically what we're going to do is we're going to use this integral notation to represent antiderivatives. Okay? That's the big idea here. There's not, we had a section, I think it was 3.9, on antiderivatives, and we didn't really have any notation. We always just said find the antiderivative of, find a function whose derivative, blah, blah, blah. We're going to use the integral sign to represent an antiderivative. Okay? So the notation, the integral of f of x dx. Okay, so notice here there's no bounds. Okay, when we have bounds, it's just some number that represents the area under the curve. When there's no bounds, this notation is traditionally used for an antiderivative of f. And is called the indefinite integral. Okay, so what does this mean? So thus, if the integral of f of x dx equals capital F of x plus c, then f prime of x is equal to little f. Okay, so for example, the integral of x squared dx is equal to x to the third over 3 plus c. Okay, so this is the same thing as saying find the antiderivative of x squared. You increase the power by 1 and divide by the new power. And then you got to remember we have a plus c here because it could shift by a constant term. Okay, so just for your notes, the definite integral which is the integral from a to b of f of x dx, is a number. The indefinite integral is a family of functions. Okay, so now let's list out, we had this table of antiderivatives that we wrote a few classes ago. Let's rewrite it in terms of the indefinite integral notation, and then we could look at an example. I know we have a quiz in 12 minutes, but we should still be able to get an example out. All right, so this is a table of indefinite integrals. The integral of c times f of x dx is equal to, you can factor out the constant. Again, these are going to look identical. It's going to look identical to our list of definite integrals as well, except they don't have bounds. So I'm going to kind of go through quick, because we just wrote these down yesterday, basically. Okay, so the integral of a sum is the sum of the integrals. The integral of a constant is equal to k times x plus c. The integral of x to the n is x to the n plus 1 over n plus 1 plus a constant. The integral of sine of x is negative cosine of x plus a constant. The integral of cosine of x is sine of x plus a constant. I know I'm going quick, so slow me down if there's one you want me to go over a little in more detail. But again, we wrote these down before. The integral of secant squared x dx is tangent. The integral of cosecant squared dx is negative cotangent. The integral of secant x tan x dx is secant of x plus c. And last, the integral of cosecant of x cotan of x is negative cosecant of x plus c. Okay, so this is just something good to have in your notes. for working out these problems. Let's look at an example. So find the integral of 10x to the fourth minus 2 secant squared x dx. Okay, and I'll write out the next one in case you could go through that first one quickly. This one says evaluate the integral of cosine of theta over sine squared theta d theta. All right, so I'll give you a couple of minutes to try to think about these. This one is pretty straightforward. This one's going to need a little bit of manipulation. You don't just find the antiderivative of each of the components, right? It'd be like if you had the derivative of a quotient. You don't just take the derivative of the top and the derivative of the bottom. There's some sort of rule that you have to follow. Same thing here with quotients, but we haven't talked about any of those rules yet. So maybe we should try to express this fraction as one of these functions. Okay, so that's how you'll deal with this one. So I'll give you a minute and a half to try to work these through. You could let me know in the chat if you had any luck with any of them. You don't have to type out your answer, but maybe, I don't know, find a funny emoji to post if you feel like you got the right answer. Navik posted a canoe of some sorts. Nice. Hopefully that means you solved it. I'll give you guys about 30 more seconds. All right, so we want to find the integral of of this function, we just do it one component at a time since they're separated by plus or minus. That's what this part says. The integral of 10x to the fourth is 10x to the fifth over 5. And the integral of negative 2 secant squared x is negative 2 tan x. And what's important to remember is there's a whole family of solutions, and they can all differ by a constant. You could simplify this fraction if you'd like, but it's not totally necessary. Okay, so this next one's definitely tougher. So let's take cosine of theta over sine squared theta. And we could break it apart into 1 over sine theta times cosine of theta over sine of theta. 1 over sine theta is cosecant theta. Cosine theta over sine theta is cotangent theta. So really what this question is asking us to do is evaluate the integral of cosecant theta, cotan theta. And that's on our chart right here. That's negative cosecant theta plus c. Okay. So yeah, again, we're going to be doing a lot with these integrals. I would recommend spending some time this weekend practicing some of them. So maybe starting the WebAssign. Because we do have a test coming up before the final. And the majority of the test will be dealing with integrals. So that seems like a good place to stop for today, right? Because we have the quiz that starts in a minute. Yeah, so good luck on the quiz. Remember, you got to smash that like button before you get out of here, especially on a quiz day, right? Think of the good luck you're going to get by smashing that like button. I'll stay around, though, and answer any questions you may have. Quiz isn't going to take you very long, so if you want to stay around and ask questions, that's fine with me. But yeah, have a good weekend. Be safe. I don't know, you know the drill. Send me an email if you want to chat about anything. We can talk on the Zoom if you'd like. I'll get out of here in case you're in the way. Should we take out the constant, like in the first one of the table of indefinite integrals? What do you mean? Oh, when should we take out the constant? Just at the end. So evaluate all the integrals and then put the constant at the end. Or is that answering your question? Or are you talking about these constants? If it's just a constant times a function, you don't have to. You could just ignore it. That's what this first part says. You just multiply on it at the end. Right. So this line says deal with each of these components one at a time since they're separated by addition. We just deal with them one at a time, and we could just ignore the scalar. So it's like, what's the integral of x to the fourth? It's x to the fifth over 5, and then we still have to remember we multiplied by 10. All right. Well, I'm going to end the stream unless you guys have any last minute questions. Thanks for coming today. We had, I think, 27 people at one point. That's pretty good. So I'll see you next week. Bye-bye.